Hello everybody, welcome back to MI212. This is Marc Gastonguay again, and today we're going to tackle our lab session on the second of our advanced pharmacostatistical topics, and that's the treatment of data below the quantification limit. There are a couple of shopkeeping items that I want to cover first, and then we'll answer some questions and then get into the hands-on example. So first, let me remind you that this week is the week where we assign your first exam. And at this point, we have included two pieces of material for that. One is this PDF file called Supplemental File for Exam. It's just a PDF file with some equations on it. The second one is a PDF of the exam questions, which you have now to start thinking about and working on. But you see here exam 1, which is the web form for entry of your exams in the exam. And I think this is still under construction. We hope to have that in place by Monday or so. But you can go through the PDF and just make notes for your answers, and then log in and enter the answers on the web form. The nice thing about this web form and this Moodle training interface is that you get immediate feedback on the exam. It's immediately graded. They're all multiple choice questions, and we ask you to please do the exam on your own. You may use your notes, lecture recordings, other materials, and so on. That's fine. But the exam is due by the end of business on next Friday. That's the 15th of October. So you have a week to complete this. It's only a 15-question exam. It's really shouldn't be that difficult. And then what we'll do on the following week, we'll review the exam questions, particularly if there are any that seem to be problematic. Okay, so if you have any questions or problems with the exam, please post your questions to the discussion board. If you feel that a question is worded ambiguously, let it be known, and we'll address that in the discussion board. And if I feel like we should reword it, I'll address that. But usually we're pretty careful to make them quite obvious, and we're not trying to trick you up here. Okay, so next I'll move to answer a question or two, and then we'll get on to SIMI and run some examples. So there's a question to further explain how maximum likelihood estimation is used for BQL data, since it's a cumulative density for the likelihood. The thing you have to remember is that maximum likelihood estimation is based on being able to express a likelihood function. Now, that likelihood function we typically deal with for continuous data is one that assumes normal distribution of measurement error, or normal distribution of the residuals. And therefore, we derive that objective function from a normal probability density function. However, if there are other expressions or other likelihood functions that are more appropriate for the data distribution, we might use those instead. For example, for data that are arising from a count of events, those are often described with a Poisson distribution. Categorical binary data are often described with Bernoulli distributions. And so we use the appropriate distribution for the type of data at hand. The key thing is that we're equating a likelihood, or at least constructing a likelihood function that is proportional to the probability of the data under the model and the parameters. So it really doesn't matter what the structure of that likelihood function is. When we deal with these combined likelihood functions, like in the case of method 4 and method 3, where we have a likelihood function for the data above the quantitation limit, and then we have a cumulative density describing the likelihood of the data that are BQL. We're just using a categorical flag to address the different forms of the likelihood for both of those. But in the first case, it's a continuous measurement, and what happens when we're dealing with continuous data like pharmacokinetic data, NONMEM already behind the scenes calculates the likelihood-based objective function. When we have these other non-continuous endpoints or non-normal likelihood functions, we need to either write out the density function ourselves or pull in a function like we use that phi function in the M3 and M4 methods. But all of this is maximum likelihood estimation. It's just that we're specifying a different functional form of the likelihood density function. Okay, so I hope that answers the question. If you still have difficulties with that, we can maybe point you to a few other references. Okay, I'm going to switch over to Simi. If there are any other questions, go ahead and post them up to the question board. And we'll get to them during a break here. And let's see, I should be up and running on Simi now. Yep. So we had provided an example set of data and a preliminary control stream for you to work with. And we have 3 examples this week. The first is one where we have a complete data set. There is no BQL data. Everything is observed. The second is one where we'd like you to deal with BQL data using a excluding the BQL data, so using a conditional likelihood that the data are above the quantitation limit. And then the third was actually implementing one of these mixed likelihoods where we actually include the BQL data, treating them as censored in some interval. Okay, so those are the 3 methods we're going to work on. I'm going to provide you the answers on the website after the class today in the folder called BQL Answers, but I think you all had a folder called bql.zip. Let me also address another minor issue that came up over the past couple of weeks with examples, and that was the inconsistency with creating the subdirectories needed here. And I have to apologize. The first time I packaged up that zip file, I did not create it so that it would automatically set the IOV mixture model subdirectory, and you had to do that manually. But we will try our best here from now on to make sure that we package those zip files so that they're always including the subdirectory that you need to work in, and you can just unzip them directly from the MI212 directory. So if you go to MI212, upload your zip file and unzip them here, we'll try to set them up so that the correct directory structure is created. That caused a little bit of confusion for some folks, and if you went back and looked at your directory structure, you'd see that there was a missing subdirectory there. But hopefully that's all resolved now. Yeah, sorry about that. We'll try to be a little more explicit the way we package the zip files. Okay, so let's move on to BQL Answers. Like I said, we had 3 examples here, and the best place to start is if we take up our, let's actually create a new window here, or a new tab for the R script, and it's called analyzebql.r. Here it is. And the other thing I'm going to open up is an R window. Okay. I'm going to also shape my windows here so that we can look at these at the same time. Okay. And as needed, we'll go back and look at the control streams. So this script walks us through the solutions here. We're going to run the BQL examples first, like we always do when we start a new session. We have to load the relevant R libraries, which include MIfuns and Lattice. So we'll evaluate those. Then we need to set the project directory. And so this is, and in fact, you don't need this, this final closing / you can do it with or without that. Make sure that you identify your username and make sure that you have this directory structure set up in your home directories. Okay, so execute that, set the project. Great. And we could set a NONMEM run file here. What we've got is the run directories are set in each of the calls to NONMEM. But you could also set that up as a variable that you set initially at the top of the script and then just call that variable name. Okay, the first one here is model 2. This is a model and data set without any BQLs. It's a complete data set. Let's take a look at the control stream. So we'll go back a page and we'll look at 2.ctl. And this is Admin 4 transform model. It's a 2-compartment model with first order input. Pretty standard implementation. We have the data set. Notice it's no BQL data, so there are no BQLs in here at all. It's all observed data, complete case history for every subject. And we have got our usual pharmacokinetic model. Here we have a covariate effect for weight on clearance, but everything else is, and as well on volume V3 and Q. Everything else is pretty straightforward. We do some derived calculations here of secondary PK parameters for this 2-compartment model system. Then some implementation of the code. Now you'll notice that a lot of these things are commented out. Well, what we're really using here is this notion IPRED equals F, so we can capture the IPRED in the data set in the table output, and then we have an exponential residual error model. That's it. The rest of this code is commented out. That's only relevant for future models. We have initial estimates for theta, each of them bounded at 0 on the low end, except for the covariate effects, which we've actually fixed here to allometric standard expressions. And then diagonal omega and sigma. We're going to call for the covariance step, which allows us to obtain standard errors. And then we're going to create an estimation run here, method 1 interaction. So this is using conditional estimation with eta epsilon interaction. We're going to create a model specification file, which we're going to store up one directory from the current space, as well as the table file and also the parameter table file. But pretty straightforward, nothing unusual about that control stream. Back to the R script, which is controlling our analysis. We're going to call non-R. Remember the command sequence here. We can have a batch of runs if we'd like, but we're just going to do a single run here, run number 2. Project's already defined. The command for NONMEM is this one here. We're going to create diagnostic plots, and we're also going to run this on the grid. Almost always you're going to leave these as defaults, but certainly always use grid equals true because we do have a grid set up here. So I'm going to evaluate that. And the job has been submitted. There are 2 components to the job. Remember, we set this up to compile first and then to execute. And that's running right now. So while that's running, let me answer another question. Question is the exponential residual model actually a proportional model executed by NONMEM? Yeah, and of course it is, because we're using analytical approximations here. So the first order approximation that we're using actually collapses that exponential residual error down to a proportional residual error. Now, if we really want to model an exponential distribution of the residual random effects, we need to log transform both sides. So log transform the data and log transform the prediction. Okay, run 2 is complete. And let's go over to the output, see what we've got. We can sort by date to see what's most recent here. Let's look at run 2. And let's look at the list file for run 2. Just echoes back our control stream here. And then let's look for the search. The kinds of things that we would be looking for here are zero gradients throughout the search, as well as gradients that are flip-flopping to very large, very small values throughout the iterations. What you want to see is that the absolute value of the gradients are consistently decreasing throughout the search. Minimization successful here. Look at our eta bar estimate. They're quite small. P-values here. Nothing really to worry about. Since we're running conditional estimation, we're also getting an estimate of percent eta shrinkage and epsilon shrinkage. Remember, this is an estimated shrinkage based on our estimates of the individual random effects and our estimate of the population variance for each of these parameters. But we get about, let's see, 0.4, 40% on one parameter, 2% on the next, and about, 0.4%, so that's quite small, 2% and 18% here on the third eta. All of those are quite small. All right, objective function is listed, and we get parameter estimates here across the board. Hard to say anything about these by just looking at these. We'll have to compare them with other runs. But so one of the things we're going to be interested in is what happens to the parameter estimates if we're dealing with this data set under a complete cases, all observed data, versus these different strategies for dealing with the missing BQL data. Another thing we can look at is a diagnostic plot, and let's see. Diagnostic plot review _2. That's for this particular run. And you see the population observed versus predicted, and the individual observed versus predicted actually looks really clean. It's simulated data, but you get the idea. You see the residuals versus predicted and weighted residuals versus predicted. The cone-shaped nature of the residuals represents the proportional variability, and we had modeled this with a proportional residual, and you see that that heteroscedastic variability looks like a constant variance when you look at weighted residuals. We call a NONMEM 7. If you specify weighted residuals, you're actually going to get the correct weighted residuals for the estimation method that you used. So we're actually getting weighted residuals here that are calculated based on the FOCE interaction assumptions. That's a nice improvement over, one of the biggest improvements over NONMEM 6. Then we have residuals and weighted residuals versus time. And then QQ plots for the distribution of the residuals. Looks pretty good. This is a decent model fit. All right, well, that was our best case anyway, because we had all the data. And no matter how sophisticated your method is for dealing with missing data, it's never going to be as good as being able to analyze the full data set. Let's go back to the R script, and we have another model to try. And that model here is 1.ctl. This is the BQL M3 method. Remember, what we're doing here is including the BQL in the data set, identifying those as BQL, but including them in the analysis as a censored data. And the assumption here is that it's censored in some interval from the quantitation limit down to -infinity. But the timing of the observation is still included here, so that BQL are somewhat informative on the objective function, whereas if we had just thrown them away, they'd have no impact at all. So let's look at the control stream there. This is 1.ctl. And the structural model is exactly the same as what we looked at with the first run. Where we get different here is in the error block. And you'll see here a little bit more complicated. What we're going to do here to implement this in a more straightforward way is to capture sigma in a theta here, and this is actually the square root of sigma squared, so it's the standard deviation of the residual error. We're going to estimate that, that's theta 10. And we're going to set a limit of quantitation here equal to 0.6 nanograms per mil. That is a constant LOQ for this whole data set, although if you had different LOQs for different studies in the data set, you could specify a variable, maybe called LOQ or LOQ limit or something, and just equate this LOQ to that variable name. IPRED is equal to F, of course, and we set up our likelihood function now. Remember, we don't need to write the likelihood for the data above the quantitation limit because that's already built into NONMEM, and that's a continuous likelihood function assuming a normal probability density. That's built into the NONMEM, and all we have to do is specify the prediction in that case. And actually, I'll skip to that first. So that's the condition here, where F flag is equal to 0. F flag equals to 0 means it's not BQL. Okay, F flag equal to 0 also indicates to NONMEM that we're dealing with a continuous density function based on normal continuous measurements. Whereas F flag equal to 1 means that we're going to set Y equal to some probability density that we're going to have to define as the user. Okay, so when Y is equal to a prediction model here, that's F flag 0. When Y is equal to a likelihood, that's F flag 1. So for the prediction model, for the data above the quantitation limit, we have a simple proportional residual error model. Okay, just like we had, well, actually we had exponential in the first run, but it collapses down to proportional due to the approximations. For the cumulative density, we have to construct that here. So it's the limit of quantitation minus the prediction divided by the variance, or sigma times IPRED. We have the cumulative density then, which is phi times this quantity, the phi function of this quantity, and that's a built-in function in NONMEM 6.2 and above. And that gives us our cumulative density here. So if the data are BQL, then we're going to describe the likelihood of those data, not a prediction for the data. Okay, and that's the setup here. The if statement here is set up for BQL values or non-BQL values. There are two if statements in there. Okay. The rest of this is pretty straightforward. The one thing we've got to do here is we've got to use Laplacian anytime we're setting part of the prediction model here to a likelihood, like we do when F flag is equal to 1. NONMEM requires that we use the Laplacian estimation option. Okay. It looks like there are a couple questions that came up on this control stream, so I'm going to set this running and then I'll answer the questions. Same options as we did for the first time here, and we'll evaluate. And I'll answer some questions. Let's see. In NONMEM 6, the length of variables still limited to 4. How about 7? In 6, it is limited to 4. In 7, you can have data item labels that are longer than that. Where can I download 1.ctl? 1.ctl is part of the zip file that we provided you on the Moodle site. I'll go back here to the course site. You see that for BQL data, BQL lab zip file, download that, and all of this content is in there. I will put the solutions up this afternoon. So we gave you the original starting point. I'll put the solutions up this afternoon after we finish class. Oh, I got a note here that our LOQ is wrong. It was specified as 0.45 in the text, and we've used 0.6 here. So we'll check on that. Might be just a typo, but of course we should be using the LOQ that was listed. couple of you picked up on that. Very, very sharp. It doesn't really make a difference for the implementation here, but of course, if the quantitation limit is incorrect here, and we have some of those points below what we've specified the LOQ, we would actually be calculating a likelihood for a slightly larger range of potential BQL data. So yeah, we should fix that. Okay, the job has been submitted, still running. Well, while that's going, let's look at the next strategy. The next one here is 3.ctl, and this is a model and dataset with BQLs commented out, just totally ignored. So this is the simple M1 method, and a commonly used method in most of our track record here in population PK. But let's take a look at that one. That's 3.ctl. Control stream looks pretty much the same on the top here, and in fact it's the identical control stream to the one that we used for the complete data set. And essentially what you're saying is, I'm going to treat this as if it's a complete data set. I'm going to ignore the BQL. Okay, so let's go back to our output. Run 1 is complete, so we'll take a look there. 1.list is in the 1 run directory. So here's our M3 implementation. Again, you're going to look at gradients to make sure that you have no zero gradients, that they're decreasing in magnitude throughout the search. And looks like we were successful. A few more iterations to do this. It says, however, problems occurred, regard them carefully and accept only after checking. So we'll take a look at that. When we write that censored component of the likelihood, it does cause some computational complexities that you're likely to maybe run into rounding errors or minimization problems, because you're asking the estimation problem to do more. But usually you can find a way to work it out. Let's see if there's any hint to that here. So eta bar estimates all look pretty good. So our etas are quite centered. Shrinkage is small again. Pretty similar to what we had observed before. We'll come back and observe the parameter estimates afterwards. But one of the things that you look at when you see that sort of a message, problems occurred with minimization, you look for parameters that might have hit the boundary, parameters being driven towards 0 or whatever the null value is. And so that's one thing I'd check on. None of the variance terms here seem to be problematic. The fixed effects parameters all seem reasonable. Remember, the allometric exponents are all fixed here. This is the residual variance. And this is the standard error of the estimates. Of course, we want to look at these in a relative term, and I'll show you a little function that we have in MIfuns that can help us to compare that. So that run looks decent. Let's look at the diagnostics. Well, our standard diagnostics here, because of the truncated likelihood, don't work. We'll create the plots afterwards, but you see at least the observed and predicted plots are shown here. The BQLs show up here. They're set at 0 in the dependent variable column. That value is not used during the fitting. It's actually just a time point that's used in that cumulative density function calculation. But you'll see them plotted here. What we could also do is go back to a script which does some plotting. I'll just run these right now. These are just set data sets, and I just want to show you the first ones. No. I still have to run number 3. That's why. Okay, let me run the models and then I'll do the plots. So the next one is the model 3, ignoring the BQLs. Set that one up. And then following that, we have model 5, which is the same sort of thing. It's the M3 method, but now allowing for combination, additive, and proportional error. That was sort of the bonus question. How do you do that? And I'll review that after answering some questions. Yeah, there's a question about, so one question here is NONMEM doesn't return residuals or weighted residuals for individuals who have at least one observation with an F flag equal to 1, meaning where at least one part of their individual record is a likelihood estimation instead of a continuous endpoint. Has this been fixed in NONMEM 7? I'm actually not sure. I know in NONMEM 6 this was a problem, and you'd have to actually go individually to calculate the residuals and weighted residuals outside of NONMEM. In NONMEM 7, we can take a look actually using, I can look at the data set or the table output. Let's go do that. So we're using in this run, method 3 was 1.ctl. So let's look at the table file, 1.tab. And I'm just gonna take advantage of the whole screen for a minute here. Yeah, here we go. See these NA values? Those are the points that are BQL in some of the individuals. But it does calculate, no, it doesn't calculate residuals and weighted residuals for any of these. Yeah, and this is not a bug. It's just an implementation option, in that what does the residual mean when you have also a component of the model that is treating that individual's data as a censored likelihood. So no, it's not solved in NONMEM 7. Just a comment that when LOQ is equal to 0.45, minimization was not successful. It is probably very well the case that this was simulated. I don't recall now. This was simulated with the LOQ equal to 0.6. It's just a typo in your handout notes. Okay. Some of you are asking about the solutions. I will be posting the solutions at the end of the lab today. The solutions are not posted yet. We've just given you the data set and a starting point. Okay. Let's see. Run 3 is complete now. Let's look at that one. 3.list. Remember, this is where we just discarded the BQL data. Runs pretty quickly. Eta bars and shrinkage all look quite similar to what we had before. Of course, we can't compare the objective function here across these models because they are different data sets or different likelihoods. So that's not a useful comparison. But we can compare parameter estimates, which we'll do in a minute. Let's look at one more model, and then we'll run some plots and do a comparison across all of these. Run number 5 here is the combination of additive and proportional residual error using the M3 method. I'll show you what that looks like while things are running. And this is 5. Everything else at the top looks the same: dollar input, dollar data, dollar subroutine, PK. Those are all constant. What happens here is that we have 2 different residual error terms, and we're modeling now the impact of those on the cumulative density function by taking the square root of the sum of the variances. Remember that the variances are additive, but standard deviations are not. So we're taking sigma squared plus sigma squared times IPRED squared for the proportional term. Okay, so that's the standard deviation squared times the prediction squared. This is the standard deviation squared for the additive component. And then what we do is take the square root of all that. That gives you an overall measure of the standard deviation of the variability at any time point. And then that just comes in here to weight the LOQ minus IPRED section of the likelihood. Everything else is the same. So the only thing we need to do now is add an additional estimation for theta 11. Okay, and specify this part of the likelihood, incorporating both residual terms. The rest is quite straightforward. Okay, so 5 is running now. And I'll give that a moment. And then we'll run a summary and some plots. But I'll turn to a couple of questions now. How does one get the weighted residual for good records? Yeah, this is not so straightforward. You can calculate the weighted residual based on the verbatim. Well, you'll need to use some verbatim code to extract the partial derivatives if you want to do this correctly, so that you weight the difference between the observed and predicted values by an overall measure of the variance. We can show you an example control stream for that. I don't have it with me right now, but I'll pull one out to illustrate that for next week. Is shrinkage of 30% small? Yeah, you know, shrinkage, it's all a relative term. Eta shrinkage is an estimated value to begin with, so it's not something you can hang your hat on, because it's based on our estimate of the variance term and our estimate of the individual random effects. It's quite possible that we could have a positively biased variance term, and that would overestimate the shrinkage. Usually the rule of thumb is that people start to get worried about using diagnostics or predictions that are based on individual empirical Bayes estimates when the eta shrinkage is 30% or greater. And that just means that that individual parameter is being tugged towards the population prior and maybe doesn't represent the individual difference all that well. It's being pulled towards the prior mean. So it's a warning sign, and it depends on how you use the individual empirical Bayes estimates in your analysis. If you're using these, and if you're using plots of etas to guide your decision making with respect to adding covariates or other things, that might be problematic. So you might want to use a different approach for building covariate models, for example. Or if you're using individual empirical Bayes estimates to predict exposure response relationships, you might be blunting that relationship if eta shrinkage is large. Okay, run 5 has completed. Great. Let's take a look. That's the control stream. Here's run 5, and we'll look at the output. So this is the same thing we did with the M3 method, but now we have combined additive and proportional residual model. Yeah, and we got successful minimization. Covariance step was aborted here. We have an algorithmically non-positive, semi-definite, but non-singular R matrix. Well, you can't invert the R matrix, so we can't get the standard covariance output. But what we can get are final parameter estimates, and they might tell us something. Yeah, so what you see here is that it's pretty obvious where the problem is that theta 11, which is the additive component of the residual error. Let me go back up to the code and show you. Theta 11 is sig 2 right here. This is the additive component. Look at the magnitude of the estimate there. Oops, sorry. Basically 9 times 10 to the minus 3. So it's quite small. That's far smaller than the range of our data. And that's probably the reason why we had difficulty with the covariance matrix. You probably have an ill-conditioned covariance matrix of the estimates, and probably obvious that it's the additive component there that's not needed. So the prior model that we ran is probably a better describer, a better descriptor of the data, or a more parsimonious descriptor. Let's do one thing here. We'll run this run log function, rlog, and this creates a summary. What we're going to do is summarize the runs that we've just done, and you can include a vector here. We're just doing those 4 runs. And what this does is it creates a file called combine run log. Here it is. And I'm going to download it and open it in Excel. Oh, it's going to open in OpenOffice. That's okay. That'll work too. This is a comma-separated text file. And it's created so that we can compare runs here. So, in fact, I'll insert a row here to put some labels. So you have first, in the first column is this description. And we don't build these labels on the fly because they can be different, and we usually do this in a post-processing step. But the first part is the description. The second part is just an indicator whether or not it's the parameter estimates or the relative standard error. So the first row, you notice there are 2 rows for every run. The first row is the parameter final estimates. The second row is the standard errors in terms of relative percent. The third is minimization status. The fourth is covariance status. If you see a 0 and a period there, those are in good shape. And then you have the objective function value. Okay, so here we look across our runs. We can't compare these. Except maybe we can compare run 1 and run 5. Those were both method 3, both with the full data set, including the BQL indicators. And you'll see the objective function didn't really change. In fact, it went up a little bit when we added the additive term. So it might be in a local minimum there, but really not that important to add that. Then we have our vector of fixed effects, and I don't remember what they are, but theta 1, theta 2, etc. And you can see here across the board that the first run here that we did is the gold standard using all the data, and we came out with a theta 1, I think that's clearance of 26.49 liters per hour, a volume of 282, peripheral volume of 297, and so on. Not too bad, and the percent standard error is quite small, 2%, 1%. Indicative of simulated data. When we go then to the M3 method, so we've now eliminated or we're dealing with a censored data set. we're still able to maintain an estimate that's quite close to our initial estimate, or the gold standard estimate. So we're getting 25.2, where the gold standard analysis would be 26. Standard error is larger percentage-wise, and that's because it's a smaller data set for one thing, and we're actually posing a more complex model. Run number 3 is the one where we just threw out the BQLs. And now we look at the estimate of clearance. That's 19 liters per hour versus 25 or 26. 26 being, again, the gold standard. 25 is the M3 likelihood adjusted censored data implementation. So you see the difference there, that now you're getting to the realm of maybe clinically significant differences in clearance estimates just by dealing with the BQL in a different way. When we go to the combined additive and proportional, the point estimates are right around where it should be, but recall the standard errors didn't run because we were over-parameterized with respect to that residual random effect. So pretty interesting here. It's a nice illustration of the impact of dealing with the quantitation of the BQL data in an appropriate, statistically rigorous manner. It's not just garbage. Those data points can be informative, and that's shown here. Next, I'm going to create a couple of plots. Sorry. Let's see. We'll go back to the R script, and yeah, we'll just create IPRED versus DV plots. Let's try this again. Yeah, for some reason my read table is not working. Ah, I know why. Because we just pasted it this way. Let's do this. Okay, now we're going to create a PDF output for some graphics, and we'll do each one of these runs for run 1, for run 3, for run 2, and then we'll do IPRED versus DV for each of those. And then by turning off the PDF device, it actually closes the file so we can look at it. It should be back here in our directory. BQL Diagnostics. So DV pred here for the BQL model. Here's the one that ignores the BQL data. Really not that different in diagnostic. And here's one for the full data. Of course, that's going to be different because you have all of these data below the quantitation limit. IPRED versus DV, these are quite similar for the full data. There you go. So as you can see, you can't really tell by diagnostic plots that there's a problem with throwing away BQLs. What's going to happen is that the model will estimate the best set of parameters it can for the data you have available. The real problem comes into actually inferences based on the parameters. So it's not prediction of the observed data, but it's actually inferences about the parameters that matters. And when we're making statements about PK parameters such as clearance and maybe the covariate effects on clearance, we want to make sure that those are as unbiased as possible. So important take-home message here is that diagnostic plots alone are not going to tell you whether or not your approach with dealing with BQL data was appropriate. So in that sort of context, you're almost left with the task of trying a more rigorous pharmacostatistical method, and then maybe a simpler method like discard the BQLs, and compare the results. If you see a noticeable or what you might deem as a clinically different result with the more rigorous approach, it probably means that you should use that approach. Diagnostic plots won't tell you. Okay, I'll answer a couple more questions. If shrinkage is large for one parameter, maybe 50% eta shrinkage, what's the better way to do model diagnostics? Well, you should not be using, or you shouldn't be putting too much faith into diagnostics that are based on the empirical Bayes estimates of the individual random effects. In other words, the eta-based diagnostics. They're not going to be reliable. So you should look at things like residuals, weighted residuals, and then simulation-based model checking. Predictive checks are a useful way, and so on. When it comes to covariate selection, in that sort of case, you don't want to use data-driven or graphic-driven covariate selection. You'd like to use pre-specified covariate relationships because, again, the empirical Bayes estimates are going to lead you astray there. So again, it's just a warning. It doesn't mean that your model is worthless. And in fact, in many cases, there's not enough information to pull that individual empirical Bayes estimate away from the population mean. It doesn't mean that your model can't be useful. It's just that you have to be careful in how you interpret diagnostics that are based on those individual etas. Okay. Well, that was the example. I'm going to wrap this up here and post these solutions to the course site so that if you want to try these or compare these to your efforts, you can do so. We have, I think I've also posted for you a reading assignment for the next week in the assignment tab. You know, again, the reading assignments are really to give you some background. We're not going to be testing you on the reading assignments, but if you have the opportunity to look at some of these papers, these are dealing with some of the issues we're going to start next week, such as nonlinear PK and parameter identifiability, as well as target-mediated drug disposition models. Okay, looks like maybe one more question. Is a numerical predictive check always better? Yeah, I'm not, you know, there's so much jargon when we talk about predictive checks. I'm sort of confused as to what people mean by different predictive checks now. You know, the original thing was a posterior predictive check, and that comes from the Bayesian literature. And then in PopPK, we've adapted that. And we hardly ever simulate from the full posterior. We would do what I call a predictive check. But then you have all of these different variations on predictive checks, and there is no one reference dictionary on what they mean. So Dan, you're asking if a numerical predictive check is better. I'm not sure what you mean by numerical predictive check. What I'm saying is that simulation-based diagnostics, no matter how you summarize them, simulation-based diagnostics are more useful than empirical Bayes estimated based diagnostics when shrinkage is large. All right, a couple more questions. Let's see. What's your suggestion if the data come with BQL equals 0 from the assay report? Ignore them or treat with 1/2, etc. Well, we've discussed this in the class on Tuesday, and we showed you which methods work better. In fact, that's the whole point of this lecture. My suggestion is that you try a comparison. Ignore them. That's the easy thing to do. And then compare something like the method 3 implementation. If you don't see a difference in the parameter estimates using those, then I think you're safe to ignore them. replacing them with the quantitation limit divided by 2, and all these things. You know, all of those data manipulative strategies are potentially biased. I would go with the simplest one, which is just drop the BQL data. Try that, and try the M3 method, and look to see if there's a difference. Okay, let me remind you of one last thing before we stop for the day, and that's to please post technical difficulty questions, problems with SIMI, problems with your login on Moodle, whatever it is. Please post them to the discussion board. Now, if you can't log into Moodle, that's one thing. You can call us directly on that. But I think everybody's okay with Moodle. That should be the place where we post questions. The advantage of doing that there is that you can see us responding to other students with similar questions, and it's also a central repository where multiple of our staff here can address your questions. So please post your technical support questions to the technical support discussion board on the Moodle course site. Okay, thanks for your attention, everyone. That's the end of our lab session for today. We'll pick up again next Tuesday with a new topic on nonlinear regression methods. Remember, you've got your exam to work on here. You have a full week to complete that. We need those submitted by midnight Eastern Time on next Friday. Have a nice weekend, everyone, and we'll talk next week. Thank you.